Welcome to Chapter 18 of our course MEC410 Design of Machine Elements. This week we're going to study springs. All kinds of springs. Coil springs, extension springs, compression springs, flat springs. And we've got 5 different homework problems for you to try out. The last 3 are given additional information that is not shown in our textbook. There's some different types of springs for you in this slide. Helical coil spring shown in the upper left. If you compress it, the coils move closer together. A helical extension spring is shown in the upper right. If you pull on the loops on the end, the spring gets longer. You have a leaf spring used for a truck suspension in the lower left. These are what are called the leaves. They're basically flat pieces of steel. And here you have a Belleville washer in the lower right corner. Take a flat washer, give it a radius, press on it from the top, and it is incredibly strong, taking sometimes thousands of pounds to compress it very little amount. Here's the geometric classes of springs. You have push springs, which are compression springs, or the leaf springs, in which you have to compress the element in order to create a force in it. You have pull springs here in the upper right, in which you apply a tensile load to create a force in the spring. You can have a torsion spring shown in the lower left, in which you apply a load via a coiling or uncoiling action of a wire of thin sheet metal. And then you have a radial spring here in the lower right, in which you exert a radial force around the periphery of the object to which they're applied, examples being garter springs, elastomeric bands, and spring clamps. Here's a bunch of extension springs that I saw at a recent trade show. They come in all kinds of different lengths, all kinds of diameters, and all kinds of coil wire thickness. These are some interesting springs. They're called wave springs. As you go around in a circle, the actual profile goes up and down as a wave. They're pretty large. This one diameter is about 2 inches. This one wave spring came across about a 16-inch diameter and could easily support my weight without compressing a whole lot. And these are flat springs, which I saw at that trade show. If you compress down on the spring, tends to flatten out the spring. Helical coil spring dimensions are defined in this picture on the left side. You have your outside diameter, which, as the name implies, is all the way across the outside of the spring. The inside diameter is all the way across the inside of the spring coil. D sub W is the wire diameter, which is the thickness of the wire that's coiled to make the spring. C is the spring index, which is the mean coil diameter, the average of the outer and the inner diameters, divided by the wire diameter. It's recommended that C, the spring index, be greater than 5 and less than 12. If you try to make it smaller than 5, you may actually crack the wire that's used to make the spring when you try to coil it. Greater than 12 and you will run the risk of buckling the spring in compression. Table 18-2 gives wire gauges and diameters for different springs. They call these springs by different names and different standards. 2 that are shown in this chart are US steel wire gauge and a music wire gauge. Extension springs have loops at the end for fixing them in place. So here's one loop, here's the other loop. You can have a twist loop, cross-center loop or hook, which is what I show in the photo. You can have a side loop or hook here. You can have extended hook, as shown here in this diagram. Or you can have all kinds of special ends. This one here where my mouse is, this one here look like eye bolts. Manufacturers can make your loop ends to your print, you're just going to pay a little more. Here's the spring force terminology. F sub s is the force at the solid length, meaning you compress the spring to its smallest height possible. F sub 0 is the force at operating length L sub 0. It's the maximum force that the spring sees in normal operation. F sub I is the force at the installed length. In this case, the installed length is greater than the operating length, and the force varies between the installed length and the operating length. F sub f is the force at the free length L sub f, and for a compression spring, this force is 0. For a linear spring, the spring rate K is equal to the change in force over the change in length, which is F sub 0 minus Fi divided by L sub I minus L sub 0. K is also equal to F sub 0 divided by LF minus L sub 0. And the type of N treatment determines the effective number of coils in the spring. The total number of coils in a spring will be called N, but in the calculation of stress and deflections for a spring, some of the coils are inactive and neglected, the ones at the ends typically. And in a spring with squared and ground ends, or simply squared ends, each N coil is active, and the number of active coils, Na, is N minus 2. For plane ends, all coils are active, N sub A equals N, and for plane coils with ground ends, N sub A equals N minus 1. The spring pitch P refers to the axial distance from a point on one coil to the corresponding point on the next adjacent coil. We've seen this notion in screws, and in gear teeth, and in sprockets. And the relationships among the pitches, free length, wire diameter, and the number of active coils are given below. We also have the pitch angle, lambda, which is equal to the tan inverse over the pitch times pi times the mean coil diameter. And this concept is similar to what we saw in a worm gear. Note that the larger the pitch angle, the steeper the coils appear to be, but most practical spring designs produce a pitch angle less than about 12 degrees. Frequently, a spring is installed in a cylindrical hole or around a rod, as in this air cylinder, and when it is, adequate clearances must be provided. When a compression spring is installed, its diameter gets larger. And so the inside diameter of a hole enclosing the spring must be greater than the outside diameter of the spring in order to eliminate rubbing. An initial diametral clearance of 1/10 the wire diameter is recommended for springs having a diameter of a 1/2 inch or greater. Table 18-3 gives different spring materials that are used. Most of them are various grades of steel, but when it comes to the leaf springs, sometimes you use the various copper alloys, which all have a good corrosion resistance and electrical conductivity. The reason is a lot of flat springs are used as terminals and connectors in electrical switches. You also have to adjust for the wire curvature. The wall factor K is a term that accounts for the curvature of the wire and the direct shear stress. Analytically, K is related to C by the formula 4C minus 1 divided by 4C minus 4 plus 0.615 divided by C. This formula applies for both the helical compression and helical tension springs. Shear stress in a compression spring is given by the equation tau, the shear stress, equals 8 times capital K, the wall factor, times the force F times the mean coil diameter divided by pi times the wire diameter cubed, which also equals to 8 times K times F times C, the spring index, divided by pi times the wire diameter squared. Let's calculate the deflection in a compression spring. Because the primary manner of loading on the wire of the compression spring is torsion, deflection is computed from the angle of twist formula. Theta equals torque times length of the wire divided by modulus times the polar moment of inertia. But for convenience, we'll use a different form of the equation in order to calculate the linear deflection F based on the typical design variables of the spring. The resulting equation is that the linear deflection F equals 8 times the force in the spring divided by the mean diameter cubed times the number of active coils and divided by the modulus of elasticity of the material in shear times the fourth power of the wire diameter. And that's equivalent to 8 times the force times c cubed times the number of active coils divided by the modulus of elasticity of the material in shear times the wire diameter. There are 3 types of spring loading for which we have data in our curves of allowable stresses. Light service is for static loads up to 10,000 cycles of loading with a low rate of loading, in other words, non-impact. We will also use the light service curve for the unusual occurrences where the spring is compressed to its solid length. Average service is the most common in our examples, and it's typical of machine design situations that have moderate rates of loading and up to 1,000,000 cycles of compression of the spring. Severe service is for rapid cycling above 1,000,000 cycles, possibly shock or impact loading, and typical of engine valve springs. Figure 18-9 shows the design shear stresses for ASTM A228 steel wire, known as music wire. There are different figures for the different types of wires. On the x-axis below is the wire diameter in inches, and on the top you can use wire diameter in millimeters. On the y-axis you have stress in KSI on the left side. On the right side you can use stress in MPa. There are 3 curves, one for each of light service, average service, and severe service. And your job is to calculate the actual stress in your spring, determine which of the 3 curves is relevant to your design situation, and as long as these curves are above the data point you calculate for the actual location of the spring stress on this graph, you're good to go. On the other hand, if your calculation of spring stress is above the relevant curve, it means you're going to have to change your design in some manner, or your spring will break before it gets to its design life. And typical ways that you change your spring design is to go with a different wire diameter and possibly a different coil diameter. Buckling can occur in a compression spring in the same manner as it occurs for a column. If you make the spring too tall and too small a coil diameter, you have this potential. Figure 18-15 shows the spring buckling criteria. On the y-axis, you plot the ratio of small f sub 0 divided by capital L sub small f, where small f sub 0 is the deflection at operating length, and capital L sub f is the free length. And on the x-axis, you plot the ratio of the free length to the mean diameter. You have 3 curves for different types of spring end conditions, where curve A, fixed ends, which is squared and ground ends on guided flat parallel surfaces, is by far the most common. you plot the location on the graph where your spring is operating, and you compare it to curve A, B, or C, whichever is relevant. And as long as your data point is to the left of the relevant curve, you don't have to worry about buckling. On the other hand, if it's to the right, or if you're way down in the lower right corner above the relevant curve, then you have to change your spring design. You can either shorten the free length if you need to prevent buckling, or you can make the coil diameter larger. Here's example problem 1 for a compression spring. A spring is known to be made from music wire, ASTM A228 steel, but no other data are known. But you are able to measure the following features using simple measurement tools. The free length equals 1.75 inches. The outside diameter equals 0.561 inches. The wire diameter equals 0.055 inches. The ends are squared and ground, and the total number of coils is 10, which means the number of active coils is 10 minus 2, which equals 8. The spring will be used in an application where the normal operating load is to be 14 pounds and approximately 300,000 cycles of loading are expected, which means the spring will be an average service application, typical of machine design, up to 1 million cycles. 300,000 cycles is far less than 1 million, so we're safe to use the average service curve. We've codified here our design input, for example, problem 1. We see that the shear modulus G is 11.85 times 10 to the 6th, and on the bottom, in the gray colored area that's in our Excel spreadsheets for input data, we've codified all the numbers per the prior slide. In step 1, we calculate the music wire gauge number, the mean diameter, the inside diameter, the spring index, and the wall factor. The mean coil diameter D sub m is equal to the OD minus the wire diameter, and that equals 0.506 inches. The inner diameter is the coil diameter, which is 0.506 inches, minus the wire diameter, which is 0.055 inches, and that equals 0.451 inches. The number of active coils is 8, which is 10 for the total number of coils minus 2. The spring index C is equal to 9.2, because that's equal to the 0.506 divided by the 0.055. The wall factor calculated per this formula as a function of C, the spring index, is 1.158. The stress in the spring at F equals F sub 0, which we call a tau sub 0, is 125,590 psi, which is calculated from this complex formula on the right. And the deflection at the operating force, F sub 0, is a 1.07 inches, which is calculated from this other complex formula here on the right. All of the input data for that formula being known at this point. In step 4, we calculate the operating length, a solid length, and the spring length. The operating length, L sub 0, is the free length, L sub F, minus F sub 0, which is the deflection for the operating length. And that's equal to 0.679 inches. The solid length, L sub S, equals 0.550 inches. That is equal to the wire diameter times the total number of coils, both active and inactive. 0.055 times 10 is 0.550 inches. The spring rate, small k, equals 13.0 pounds per inch, which we calculate from the force at the operating length divided by the deflection, which is the change in length at the operating length. The force at the solid length, F sub S, is equal to 15.69 pounds, which is the spring rate times the difference between the free length and the solid length. The stress in the spring at a force of the solid length is called tau sub s, and that's 140,782 psi, the largest stress that we see in the spring, and that's ratioed up from the operating stress by the factor capital F sub s divided by capital F sub 0. In step 6, we use the design stress for the material, then compare it to the actual operating stress. We are operating here on the average service curve for our design stress, and we plot on this graph a point that corresponds to the stress in the spring on the y-axis, which is a 125,590 psi, and on the x-axis we have the wire diameter, 0.055 inches. And because that point is below the average service curve, we're good to go. Then we calculate in step 7 the maximum permissible stress and then compare it with the stress at the solid length. And for this exercise, we use the light service curve, the top one, and we plot a data point that has a y value of 140,782 psi and an x value of a 0.055 inches, and that data point is below the light service curve. Therefore, the stress at the solid length is acceptable. In step 8, we check the spring for buckling and coil clearance. We use curve A because this spring had squared and ground ends. And we plot a data point which has for the x-axis 3.46, and that is equal to the free length L sub f divided by the mean coil diameter. So 1.75 divided by 0.506 is equal to 3.46. On the y-axis, we plot the ratio of the operating deflection divided by the free length, which is 0.61 up here. And we find that this data point is to the left of curve A, and therefore the spring will not buckle. In step 9, we specify a suitable diameter for a hole in which to install the spring. The coil clearance formula, CC, equals the difference between the operating length and the solid length divided by the number of active coils, which calculates to 0.016 inches. The minimum coil clearance, CC minimum, is equal to the wire diameter, 0.055 inches, divided by 10. That is 0.0055 inches. Therefore, the coil clearance is acceptable. 0.016 is greater than 0.0055. The diameter of the hole must be greater than the sum of the outer diameter of the coil plus the wire diameter divided by 10. And when we calculate that number, we get a minimum hole diameter to insert the spring of 0.567 inches. Let's study example problem 2 to design a compression spring. A helical compression spring is to exert a force of 8 pounds when compressed to a length of 1.75 inches. At a length of 1.25 inches, the force must be 12 pounds. The spring will be installed in a machine that cycles slowly, and approximately 200,000 cycles total are expected. The temperature will not exceed 200 degrees F. The spring will be installed in a hole having a diameter of 0.75 inches, and for this application we want to specify a suitable material, wire diameter, mean diameter, OD, ID, free length, solid length, number of coils, and type of end condition. We will check the stress at the maximum operating load and at the solid length condition. The procedure works directly toward the overall geometry of the spring by specifying the mean diameter to meet the space limitations. The process requires that you have tables of data available for wire diameters, graphs of design stresses for the material from which the spring will be made. We will make an initial estimate for the design stress for the material by consulting the charts of a design stress versus wire diameter. In general, more than one trial must be made, but the results of the early trials will help you decide the values to use for later trials. In step 1, we specify a material and its shear modulus of elasticity G. For this problem, we can use several different standard spring materials, but we've selected ASTM A231 a chromium vanadium steel wire for this example. G equals 11,200,000 psi. We identify the operating force F sub 0 in step 2, the length at which the force must be exerted, L naught. The force at some other length, which we call the installed force F sub I, and the installed length L sub I. Remember that F sub 0 is the maximum force that the spring experiences under normal operating conditions. Many times, the second force level, F sub I, is not known. In that case, you let F sub I equal 0 and specify a design value for the spring length LF in place of Li. But in our example, we do know F sub I and L sub I. F sub I equals 8 pounds, L sub I is 1.75 pounds, F sub 0 is 12 pounds, L sub 0 is 1.25 inches, and all this information is codified in the table at the bottom of the slide. In step 3, we compute the spring rate K equal to F sub 0 minus F sub I divided by L sub I minus L sub 0, which equals 8 pounds per inch. And we calculate the free length L sub F equal to L sub I, 1.75 inches, plus F sub I divided by K, which is 8. The free length L sub F equals 2.75 inches. We're going to use an average service, which is approximately 200,000 cycles, to estimate a nominal design stress for the spring. And we chose 130,000 psi, which of course is strictly an estimate, as what you'll see soon, a rather high estimate. And we'll check the stress later to make sure that the stress is less than the average service stress for the wire diameter we've picked. The minimum hole diameter is 0.75 inches, and so we've assumed for now a trial mean coil diameter of 0.6 inches. In step 7, we compute a trial wire diameter by solving equation 18.4, which is normally for shear, but we turn this equation around in the bottom right corner and we calculate an equation for the wire diameter as a function of the design shear stress. Everything else in that equation in the lower right corner is known except for a wall factor, because the wall factor depends on the wire diameter. But wall factor K does not vary much over the normal range of spring indexes C. Between spring indexes 5 and 12, we see that the wall factor is between 1.1 and 1.3. So we take a guess in between the range of 1.2, and it'll be checked later. And at the bottom, we can calculate a wire diameter d sub w of 0.055 inches based on the other numbers in the equation for d sub w. But there's a catch. We can't necessarily buy a spring with a wire diameter of 0.055 inches. So we're going to need to look at the standard spring wire diameters and pick the one that's a little bit above it. When we look on our chart, we see that US steel wire gauge, which is what we're using, has a 0.0625 inch gauge, which is above the 0.055 inches, and so we select it. When we substitute 0.063 inches for the wire diameter, we see based on our loading curve for ASTM 231 material that the nominal operating range or average service cannot exceed 145,000, and the stress for the solid length of the spring is compared to the light service curve, and that stress cannot exceed 170,000 psi. To continue in step 9, we compute the actual values of C and K. The assumed trial mean coil diameter was 0.6 inches, and dividing by the specified wire diameter of 0.063 inches, we find the actual spring index will be 9.6, from which we can calculate an actual wall factor K of 1.15. In step 10, we compute the actual expected stress due to the operating force F sub 0. In the lower right corner, we give you all of the values that we use to calculate this shear stress in the spring at F sub 0. That's 86,459 psi, which is well below the 145 ksi number for the average service curve, so we're good to go. In step 11, we compute the number of active coils required to give the proper deflection characteristic for the spring. And solving for n sub a, when we do a little bit of algebra, we see that the number of active coils equals g times a capital D sub w divided by 8k times c cubed. That I'm pointing out with my mouse. We get a number of active coils is 12.36. We can then compute the solid length, L sub s, the force on the spring at the solid length, capital F sub s, and the stress in the spring at solid length, which is tau sub s. And this computation will give us the max stress that the spring will receive. The solid length, L sub s, is 0.898 inches, which is the wire diameter times n sub a plus 2 inactive coils. The force at the solid length is then the spring rate times the difference between the free length and the solid length. That's 14.8 pounds. And then the solid shear stress in the spring is ratioed up from the shear stress in the spring at the operating length by the factor capital F sub s divided by capital F sub 0. And that's 106,768 psi, which is well below the design stress here of 170,000 psi that's in the light service curve. So again, we're good to go with the maximum stress in the spring at the solid length. In step 13, we can compute other geometric features and compare them with space and operating limits. The hole diameter to insert the spring is 0.750 inches, and calculating the actual outer diameter, we get only 0.663 inches, so clearly this spring will fit in the hole. We then calculate the x and y values for buckling. X is 4.58, that's here. Y is 0.55. And this data point is to the left of a curve A for squared and ground ends on a guided flat parallel surface, so we're good to go for buckling. Here is an Excel worksheet on the next 2 slides that gives you the full solution to the problem. There is a good deal of common data between extension and compression springs. The U.S. steel and music wire dimensions for wire gauges, the material properties, the formula for spring rate K, spring index C, pitch P, pitch angle lambda, shear stress tau, wall factor K, and deflection F. And the graphs for design shear stress are common too. So we won't go over that information for extension springs. We'll just focus on the unique information for extension springs that is not found in compression springs. And the big one is unique aspects of the extension spring in the design of the hooks and loops on the end. The idea is you have to pull on an extension spring and you need something to pull on. And what you pull on is these curved extra loops put in at the extension spring ends. These springs are designed to exert a pulling force and to store energy. They're made from a closely coiled helical coils similar in appearance to helical compression springs. Most extension springs are made with adjacent coils touching in such a manner that initial force must be applied to separate the coils. And once the coils are separated, the force is linearly proportional to the deflection as it is for the helical springs. Figure 18-19 in the upper left shows a typical extension spring, and figure 18-20 on the upper right shows the characteristic type of load deflection curve. By convention, the initial force, capital F sub F, for an extension spring is found by projecting the straight line portion of the curve back to zero deflection. So that's this small area of the curve. Initial attention should be controlled to 10 to 25% of the maximum design force. And to do this, we plot a curve of the max and minimum torsional stresses due to the initial tension as a function of a spring index C. And the idea is that your design should have a torsional stress due to initial tension somewhere in this range between the two lines. Example problem 4 for designing an extension spring will help you understand these details. A helical extension spring is to be stalled in a latch for a large commercial laundry machine. When the latch is closed, the spring must exert a force of 16.25 pounds at a length between attachment points of 3.5 inches. As the latch is open, the spring is pulled to a length of 4.25 inches with a maximum force of 26.75 pounds. An outside diameter of 5/8 of an inch, which is 0.625 inches, is desired. The latch will be cycled only about 10 times a day, and so the design stress will be based on average service. We will use ASTM A227 steel wire. We dial all of this information into the table at the bottom of this slide. The shear modulus G for A227 material is 11.5 times 10 to the 6th psi. In step 1, we will assume a trial mean diameter of 0.5 inches and a trial design stress of the spring for 110,000 psi. We will then compute a trial wire diameter from equation 18.4 for the maximum operating force, assuming the mean diameter of 0.5 inches, the trial design stress of 110,000 psi, and an assumed value of wall factor K of 1.2. And this assumed wire diameter is 0.072 inches, which is very convenient indeed because it corresponds to US Steel 15 wire gauge, which is also 0.072 inches. The estimation of design stress from figure 18.8 is shown here. The actual design stress of the wire comes out to 121,000 psi on our curve at a wire diameter of 0.072 inches. In step 4, we compute the actual values for the outside diameter, mean diameter, inside diameter, spring index, and the wall factor, and that's shown here throughout the table, and this calculation is very similar for the compression spring. And we calculate an actual expected stress in the spring under the operating load of 120,335 psi, which is slightly below the design stress on our curve of 121,000 psi, so this solution is acceptable. In step 6, we compute the required number of coils to produce the desired deflection characteristics. We solve equation 18.6 for the number of coils, and we substitute spring force K equals force over deflection, which is capital F divided by small f. We can then compute the body length for the spring and propose a trial design for the ends. Our body length is calculated at 1.25 inches because that is the wire diameter of 0.072 inches times the number of active coils plus 1. So that's right here. And our assumed value of free length of LFA equals 2.21 inches is calculated from this equation, the body length plus 2 times the inner diameter. And for now, this assumed value of the free length is only an estimate. It's not going to be the final value. In step 8, we compute the deflection from the free length to the operating length, which is 2.04 inches. And we compute the initial force in the spring at which the coils begin to separate. This is done by subtracting the amount of force due to flexion, small f sub 0. And what we find in the second row of the spreadsheet is the trial initial force, capital F sub I, is minus 1.83 pounds, which is impossible. And what it means is that our assumed estimate of a 2.04 inches for deflection from free to length at max force cannot be possibly right. We now select a new value of the free length, capital L sub f, of 2.55 inches, which is roughly 20% higher than our initial 2.04 inches, and we try again. Now we get that the second trial deflection from free to length at max force is 1.7 inches, which then calculates out to a second trial initial force of positive 2.95 pounds, which is reasonable now. We then compute the stress in the spring under the initial tension and use figure 18-21 to see if we are inside the preferred range. Here's our spring index on the x-axis, and the stress in the spring at F equals Fi is 13,271, which is just above the lower limit line, and thus this is an acceptable solution. And here's your full solution to example problem 4, shown in Excel worksheet format. The moment in a helical torsion spring should make the coils tighter. And this moment should act in a direction that causes the coils to wind more tightly in order to make them tighter, rather than to open the spring up. This takes advantage of the favorable residual stresses in the wire after forming. In the free or no load condition, the definition of mean diameter, outside diameter, inside diameter, wire diameter, and spring index are the same as for compression springs, so no need to repeat that information. But torsion springs have different equations for the mean diameter and the number of coils. As the load on a torsion spring increases, its mean diameter d sub m decreases and its length L increases, according to the following relations. dm equals a dmi times n sub a divided by the quantity n sub a plus theta, where a d sub mi equals the initial mean diameter at the free condition, Na equals the number of active coils in the spring, and theta is the angular deflection of the spring from the free condition, which is expressed in revolutions or fractions of a revolution. Length L equals a dw, which is the wire diameter, times the quantity of the number of active coils plus 1 plus theta. And this equation assumes that all coils are touching. Torsion springs must be supported at 3 or more points. They're usually installed around a rod to provide location and to transfer reaction of forces to the structure. And the rod diameter should be approximately 90% of the ID of the spring at the maximum load. In this hand gripper, there is your diameter of the wire that is going into these loops. You squeeze on the handles and then you compress the springs in the torsion spring, and then you decrease the mean diameter in the spring. Here in this structure you can see more clearly there is the coils of the torsion spring, and there is a pin right down through the coil. And of course, here is a very ancient coil spring used for a laundry clip where you can hang your clothes out to dry. The bending stress is created in a torsion spring. And the stress in the coils of a torsion spring is bending stress because the applied moment tends to bend each coil into a smaller diameter. This is shown here at the bottom. And the stress is computed from a form of the flexure formula, sigma equals mc over I, modified to account for the curved wire. And because most torsion springs are made from round wire, the section modulus I over C is S equals pi times the wire diameter cubed over 32. And then using the substitutions in this equation 18-19, we see that sigma equals 32 times the moment times the K sub B curvature correction factor for bending divided by the quantity pi times wire diameter cubed. The curvature correction factor is reported by Wall from this equation 18-20, where C is the spring index. The angular deflection is calculated from the bending stress equation. And the basic equation for the angular deflection is theta prime equals m times L sub w divided by EI, where theta prime is the angular deformation of the spring in radians, m is the applied moment or applied torque, L sub w is the length of the wire in the spring, E is the tension modulus of elasticity, and I is the moment of inertia of the spring wire. And by performing substitutions for L sub w and I and converting radians to revolutions, we see that the angle theta, using the substitutions in equation 18-21, is 10.2 times the moment times the mean diameter times the number of active coils divided by the quantity tensile modulus of elasticity times wire diameter to the fourth. Torsion springs have their own design stress curve. Same concept, light service, average service, severe service. Stress is on the y-axis, wire diameter on the x-axis, but the curves are at different values of stress and have different slopes. Here's example problem 5 for a torsional spring. A timer incorporates a mechanism to close a switch after the timer rotates one complete revolution. The switch contacts are actuated by a torsion spring that you're going to design. A cam on the timer shaft slowly moves a lever attached to one end of the spring to a point where the maximum torque on the spring is 3 pound-inches. At the end of the revolution, the cam permits the lever to rotate 60 degrees suddenly with the motion produced by the energy stored in the spring. At this new position, the torque on the spring is 1.6 pound-inches. But because of space limitations, the OD of the spring should not be greater than 0.5 inches, and the length should not be greater than 0.75 inches. Using music wire ASTM A228 steel wire, the number of cycles in the spring will be moderate and use design stresses for average service. All of this information is dialed into the Excel chart shown at the bottom of the slide. And here's all your calculations for the first part of the solution. We show how we take the assumed trial mean initial diameter of 0.4 inches and an assumed design stress in the spring of 180,000 psi, an assumed wall factor of 1.15, and an assumed wire diameter of 0.058 inches, which rounds up to 0.059 inches because it corresponds to music wire 25 gauge. We then recalculate the wall factor based on the actual values for wire diameter, outside and inside diameters, and spring index, and we see that the wall factor is 1.123 as opposed to 1.15. We then plot our actual stress on the curve shown here for music wire. And we see that at 0.059 inches and our stress of roughly 170 KSI, that it's below the point on the average service curve, and so it's an acceptable solution. And here's the second part of the solution to example problem 5, where we calculate the rotation spring constant, 8.4 pound-inches per revolution, and the actual number of coils. And we go through some other calculations that are in our textbook for contribution of the ends of the spring and number of coils in the body, N sub B. Eventually, we recalculate the mean diameter at the max operating torque, which is 0.387, and recall that that diameter is not the initial diameter, it's actually smaller. The length of the spring with all coils touching, meaning the maximum of the spring when you're at the maximum operating torque, is then 0.685 inches, which is still less than our spec of 0.75 inches, and so this is a successful solution.